Hello everyone, welcome to Prime Number. We've talked about the Bitcoin, how does it work, we talked about Bitcoin transactions, and a lot of cryptography concepts. So it's time to talk about the Bitcoin blocks. The Bitcoin blocks is a processing unit to process a bunch of transactions in a whole and append it to the blockchain. So if the Bitcoin process each individual transaction at a time and append to the blockchain, the performance would be even much poorer than the current one. So, but we have to prevent each individual node to broadcasting the blocks in a massive way that it confuse the blockchain which one should be appended to the longest chain, and to prevent to causing a lot of soft fork. So that's why the Bitcoin also introduced a way to slowing down the process, like slowing down the producing of the blocks. We call it the consensus algorithm, but it's actually not really a consensus, but a way to prevent soft fork, to only approving one single block to be appended to the blockchain. Let's take a look what's in the Bitcoin blocks, what is the Merkle tree, and how it works. A Merkle tree is a tree that every leaf node is labeled with the hash of the data block, and every non-leaf node is labeled with the cryptographic hash of the labels of its child. Here we have, for example, transaction 1, transaction 2, transaction 3, and 4. So those are transactions which holding a big chunk of data like inputs and outputs, and we calculate each transaction with a hash value. For example, this is hash 1 and hash 2. So this hash value is actually the transaction ID, which is also the hash value. So for this case, the miner don't need to actually do the hashing because it's already in the transaction ID. So this is the ID 3, ID 4, ID 2, and ID 1. So treat those hashes as the leaf of the Merkle tree, and basically a Merkle tree is a binary tree, so the non-leaf node is a combination, is doing a hash and concatenate the hash of the nodes of the two leaf node. So that would be a hash of the hash of transaction 1 plus the hash of transaction 2. The same thing for 3 and 4 is it will do a hash of the hash of transaction 3 and hash of transaction 4. And we do it recursively until it come up with only one root node, which is also here is the hash of hash 1, hash 2, plus hash of hash 3 and hash 4. Okay, so this is the Merkle root. And the Merkle tree allow a very efficient and secure verification of the content of large data structure. So as you can see here, if you change anything in any of these transactions, those values would get changed and will be propagated until to the root. So we'll get a very different Merkle root. So just verify the Merkle root is a very simple way to verify the content of all those transactions. How does the Bitcoin node produce a block? So here we have, this is a miner. It's a Bitcoin node. So miner received a transaction, like all the time. The transaction can coming from a wallet or it coming from another node. So this is from another node. This is a transaction 2, which is they get relayed and keep going. It will get a list of transactions in the pool. So the miner will, or basically miner incentivized by producing blocks. So the miner want to get not only the Coinbase coins, but also the transaction fees. So it will order the transaction, which one has larger size or bigger amount of the transaction fee. So it will pick up several transactions. So nowadays, a block may contain hundreds to thousands of transactions in a block. So for example, this miner choose this 4 transactions, and what it does is it needs to form a new block. So in the block header, you have the field, the Merkle root, which is I talked about before, is the combination of those hashes. So this get a hash of all the transactions. It put into the Merkle header, and it will also come up the first transaction, which is the Coinbase transaction. So remember, the Coinbase transaction, we talked about this earlier, is how the miners create coins. This transaction will actually create coins. It doesn't have any input, so the input is no, and output is how much coins you will get for producing this block. So right now, initially, you'll get 50 BTC, and when the halving starts, it will get 25, and this we're at the third halving, so that we get 12.5. So you got 12.5 BTCs here, and this is also a transaction. Let's put into the first one, and the miner is also responsible for validating all the transactions, such as if there's any transaction missing the output part of the transaction, if the input which the transaction referencing to, the output has already been spent, if the crypto signature of each input is valid, and as we talked before, if the Bitcoin script can be successfully executed without any errors, if the Coinbase value is bigger than the sum of the block creation fee and transaction fees. If it's bigger, then it will be rejected. After doing all those validations, now it comes to a harder part to form this block. So in the block, there is a value called nonce, which is basically a number the miner has to come up to calculate the hash of the block. The nonce can be any number, 1, 2, 3, and include the nonce. The nonce is in the block header into the block. The miner can come up with a bigger hash, right? So the bigger hash value has to meet the criteria, like how many zeros, how many leading zeros. So as we talked before, the hash value would be dramatically different. Just do a minor change of the bits in the block. So with a minor change of the nonce, you will get a very different hash value. But given tons of the hash value you get while changing this, the chance you will get for the hash value starting with like a number of zeros. Like I can adjust the difficulty, how much time it takes to produce a block by require how many leading zeros of those hashes. So let's say we require 10 zeros before the other characters in the hash.
So you have to calculate a large amount of hash and then come up with something. For example, something like this, blah blah blah. And then once you get it, you actually successfully produce the block. It meets all the requirement, all the transaction is valid, and then you need to relay this block, same as you relay your transactions to other miner. You will put this into the others miners. You will relay this to other miners, and other miners will keep relaying. So before the other miner keep relaying this transaction, they will do the same validation again. By keep doing that, eventually in the Bitcoin network, the majority of the miners will have your block. So for example, this is the original block, the block tail, and this is new block. So after doing this, all the miners will have this new block appended to the previous block and repeatedly, so that your data, your transactions will be recorded in the blockchain. So the following blocks, which produced maybe by another miner, will append to your block later. By keep doing that, so the blockchain is keep growing. So right now, so there's a concept called the block height. It's like how many blocks has been produced since the Bitcoin was born. So right now, it's pretty close to 600,000 blocks has been produced. Okay, now let's take a look at the real block. So this is the block I randomly pick up today, and you can see here it has 933 transactions. The total output, which including payment to itself, is 1,626 Bitcoin, and this is the estimated transaction volume, which not including the payment to itself, that's 220 Bitcoin, and the transaction fee is 0.05 Bitcoin, and the height is how many blocks in the total history. There's close to 600,000. This is the timestamp, this is relayed by, and this is the difficulty and the bits. Those are the difficulty rules. This is the block size, this is the weight. So the weight limit should be 4 million weight unit. So this is about 2.5 million. And the version, and nonce is the one actually the miner need to guess in order to produce the block. This is the important piece of the proof of work, so that you have to do some work before you get authorized to add to the blockchain. And the block reward is 12.5 BTC. So every 4 years there's a Bitcoin halving happening. So the first halving was happening in 2012. So starting from 2009 to 2012, the incentive is 50 Bitcoin, and from 2012 to 2016, that's 25 Bitcoin, and now it's 12.5 Bitcoin, and we're having a next halving in next year. So you will see here list all the transactions. Well, I'm not diving into each individual ones, but you can see here we have unable to decode output address, so maybe we can dive into that. So this is the raw data of the block. As you can see, well, there's some information is not extracted in the website. So the confirmation is how many blocks already appended after this block, and strip the size version, the Merkle root. So this is actually a hash root of the hash tree of all the transactions. And this listing all the 900 something transactions. So the verification is checking the first transaction has to be the Coinbase. So the Coinbase transaction is the transaction to create the Bitcoin as an incentive to the miner itself. So as I mentioned in my first episode, the Coinbase field referencing to the headlines in the Times back to 2009. And as you can see, the input is the Coinbase, and the output, the first output index is the coin itself. So it paid to this address, and this is public key hash, and the index 1. So as I mentioned in my last episode, so when Bitcoin add the segregated witness, so it introduced another structure which is also a Merkle tree that combine all of the witness data, and the hash root of the witness is put into the output of the Coinbase transaction. Since you cannot change the header, otherwise that would introduce another hard fork which will introduce another coin, so you don't want to do that. So the compatible way is to changing the output of the Coinbase, which is you only have one Coinbase transaction, which can be treated as a metadata of your block. So the OP return, which means this output is you treat it as invalid, so that you don't have to execute it, you don't have to redeem anything inside of this output, and you can put any data you want. Well, there is a length limit, but arbitrarily speaking, you can put anything into this output. So they put the Merkle root of the witness into the output of the Coinbase transaction. And here comes a whole list, a big list of the blocks. Let's see. So it's really a lot of data. And this is the end. So this is the header. The time, the median time is the median time previous, I believe it's 10 or 11 blocks. So this time has to be larger than this time, otherwise it would treat this block as invalid. Nouns, the bits and difficulties, how hard the proof of work is, number of transactions, previous block hash, and next block hash. So this is referencing to the previous one, and this is referencing to the next one.
We have talked about the Bitcoin blocks, the transactions. Maybe we should talk about the consensus algorithm next time, the proof of work. Thanks for watching. Comments below what you want to see in my channel, and see you next time.